So far in nuclear physics, till now we have discussed the nuclear forces. As you have seen that the nucleon force which binds the nucleons in the nucleus is very complicated. It is very different from the known electromagnetic and gravitational forces which obey the inverse square law. But you know, the nuclear force does not obey the inverse square law. There is no particular relation between the nuclear force and the distance between the two nucleons between which this force acts. Actually, the nucleon force is found to be very strong, but it is of short range. You have seen that this force is effective only when the distance between two nucleons is almost of the order of femtometer, that is, it is almost equal to 1.4 femtometer, and along with the attractive nature, this force is also repulsive when the separation between two nucleons is less or equal to 0.4 fm. Then you know, if there are two nucleons, there is either two neutrons or two protons, or one neutron and one proton, and the separation is of the order of 0.4 fm, then actually this force becomes repulsive. So you can say that this force has a repulsive hard core, and at the same time, you know, this force includes exchange forces, non-central forces, and velocity dependent forces. In fact, when you have studied the nuclear force, you have seen actually there are three different approaches to understand the nucleon potential. And what are those three different approaches? You have seen the first one is actually known as phenomenological approach. The second is the famous meson theory proposed by the Japanese scientist Yukawa. And the third one is the most recently developed quark theory. Although we have studied in the previous lecture about the phenomenological approach, in which we have studied different scattering experiments, and by those scattering experiments you have found the different characteristics or nature of this nuclear force. But we have not studied till now quark theory. Actually, when I will start the topic on elementary particle, then we will see the quark theory of nuclear force. In fact, the discussion of the nature of nuclear force is a separate topic which we have already studied partially. But now our aim is to discuss the another important chapter on nuclear physics, and that is actually the nuclear models. In fact, as the nuclear force is very complicated, so with such a complicated nucleon potential, it is rather a difficult task to attempt any meaningful solution to many body problem such as a complex nucleus. As you know, a nucleus contains a large number of nucleons, and so to make a rigorous treatment, it is very difficult to develop a theory. And in this regard, so many phenomenological models have been developed to describe the nucleus. Actually, these models are slightly different from one another and are highly successful in explaining the extraordinary or contradictory features that the different nucleus exhibit. In fact, each model is limited in scope and they do not agree at all levels to each other. When you talk about the nuclear models, you will see that broadly we can classify the nuclear models in the following group. The first one is known as independent particle models and the another is collective models. This is actually the broad classification, although there have been developed a large number of nuclear models which we will see separately. Actually, among these, the simplest model is the independent particle model, and this is in this independent particle model, one of the model is known as Fermi Gas Model, in which nucleons are assumed to behave as an ideal non-interacting Fermi gas. When you say Fermi gas, it means the particles of which obey the Fermi-Dirac statistics. So one of the model of independent particle model is Fermi gas model. In fact, a better approximation is to consider the nucleons to move independently in a common potential well, such as the oscillator potential or the square well potential, or more realistic Wood-Saxon potential. In fact, the harmonic oscillator potential is more popular since it can yield analytical solution to many nuclear problems. If the nucleus is deformed, then one can use a Nielsen type of deformed potential to study the nuclear model. By introducing the spin-orbit coupling, one can obtain the single particle energy levels which exhibit a shell structure in accordance with the magic numbers observed experimentally. In this lecture, first of all, we will see the evidences for these magic numbers. You will see just now. The shell model actually works well for nuclei with closed shells or with a few nucleons outside the closed shells. For nuclei midway between the closed shell and collective excitations are more probable. Some nuclei exhibit rotational spectrum, some other vibrational spectrum, and a combination of both. Shell models are collective models which deals with idealized situations that are contradictory in nature, and for certain nuclei, a blending of both of these aspects, which is called actually unified model, seems to yield better results than the other models. So first of all, I have given just in a tabular form the different models which have been developed till now, and as I have told you that in broad sense we can classify the nuclear models in two classes. First one is called independent particle model and the another is called collective model. Now in this independent particle model, the important models are Fermi Gas Model and the optical model, and along with it there is another important independent particle model is the shell model, which is our core interest to discuss in the present lecture series. And when we will study actually the shell model, we will study two types of nucleus. The first of all we will see the spherical nucleus, and after that deformed nucleus, and this deformed nucleus is also known as Nielsen model of nucleus. And in collective models we see the liquid drop model, and after that rotational model, vibrational model, and rotational vibrational model. And as I have told you, just as a combination of these models we will study the unified model and the superfluid model, although this superfluid model is also the independent particle model. So these are the different models, but in present lecture series we have to study first of all the most important model of nucleus, which is actually called cell model of nucleus. So let us start to deal with the cell model of nucleus. So after this short introduction, I am just going to start to know the main feature of this nuclear cell model. We will divide this lecture in a large number because this is a very vast concept. So this cell model will be completed in not in 1 or 2 lectures, but this will contain so many lectures, and after those lectures you will have a complete idea of this nuclear cell model, all of these facts, its predictions, its observations and explanations. So what is the main fact of this nuclear cell model? In fact, you have studied definitely in atomic physics the Bohr model of atoms. In Bohr model of atoms you have studied that in an atom there is a positively charged nucleus, and about that nucleus in different circular orbits electrons revolve due to the electrostatic attraction of the nucleus. It means the extra nuclear electrons are arranged in different cells in accordance with a particular selection rule, that is the formula 2n square. The electrons are distributed in different cells and subcells, and among these cells and subcells, you know, there are closed cells or completely filled cells, and also the outermost cells are not completely filled, but the number of electrons present in those cells are less than they can accommodate. On the line of this Bohr model of atom, a nuclear model for the nucleus has been developed, and that is called actually the nuclear cell model. So you can say, by an analogy with closed cells and subcells, in case of atoms, it is assumed that the nucleons also form similar closed cells as the electrons form the closed cells and subcells. Similarly, it is assumed in this model that the nucleons are also distributed in different cells and subcells, among which some cells are completely filled by the nucleons, which are called closed cells, or the subcells. In fact, the neutrons and the protons, which constitute the nucleus, are supposed to arrange in some type of cell structure, and these cells get closed with a suitable number of protons, as the atomic cells are closed by a suitable number of electrons. Similarly, the nuclear cells are assumed to be closed or completely filled with a suitable number of protons and neutrons. In fact, in this model, it is assumed that each and every nucleon moves independently inside the nucleus in a fixed orbit, just like electron. As you know, electron moves in a fixed orbit. So in this model, it has been just compared with this atomic model, that the nucleon also moves independently from one another in an orbit, and what is the potential or what is the force which is responsible for the motion of these nucleons in different orbit. In this model, it is assumed that these nucleons are influenced by a central field of force or central potential V of R produced by the average interaction between all the remaining A-1 nucleons. What does it mean? It means if you consider that the total number of nucleons in your nucleus is A, which is actually also called mass number. This A is actually the sum of the number of protons, which we denote by the symbol Z, and the number of neutrons. So if you consider one of the nucleon to move in an orbit, the force which is responsible to move this nucleon in orbit is provided by the remaining nucleons. So if you consider one nucleon, the number of remaining nucleon will be what? This will be A-1, because there are total A nucleons and one is revolving in an orbit. So the remaining number A-1 of the nucleon provides the necessary force to revolve this nucleon in the cell or subcell. In fact, these are the basic feature of this nuclear cell model or independent particle model. In fact, the rigorous theory for this nuclear cell model we will develop in the forthcoming lecture. But first of all, we will see here the concept of magic numbers. In fact, you know that two scientists, Bruckner and Bethe, have made attempts to deduce the properties of nuclear matter and also the finite nuclei from the fundamental nucleon-nucleon interaction using very complicated formulation. The cell model of nucleus, which we wish to discuss as an independent particle model, has achieved amazing success in certain predictions, and this model at first appears to be incomplete with nature of the nuclear force. This theory, although introduced phenomenologically without any theoretical basis here, but now in view of its successful predictions, you will see that this theory actually satisfies, or this is just a justification of the Bruckner's theory of the nucleon-nucleon interaction. So first of all, we will see the evidences for the nuclear cell structure, and in this regard we will see first of all the idea of magic numbers. In fact, you know, the simplest evidence for the nuclear cell model comes from the discovery of magic numbers. And what are these magic numbers? These magic numbers are 2, 8, 20, 28, 50, 82 and 126. You must remember these numbers. These numbers are called magic numbers. In fact, any nucleus which has a number of protons like 2, 8, 20, 28, 50, 82 or 126, or number of neutrons, either number of protons or number of neutrons, and those numbers are 2, 8, 20, 28, 50, 82 and 126. Those nuclei are called actually the magic number nuclei, or simply you call it magic nuclei. In fact, why it is called magic nuclei, you will see that such nuclei exhibit some extraordinary property in comparison to the neighboring nuclei. We will see this just now. So I have mentioned it here that the nuclei having magic number of neutrons or magic number of protons are called magic nuclei. It means what is a magic nuclei? A nucleus which has either number of protons or number of neutrons just equal to the magic numbers, then you will call that nucleus a magic nucleus. Okay. In fact, these magic nuclei have some different properties from the nuclei with neighboring values of n or z. These magic nuclei are just like the inert gas atoms. And you know, in case of inert gas atoms, all the cells are closed. For example, helium is an inert gas, and this helium is 2He4, and its cells are completely filled, closed cells. Just helium, just like that, there is neon, there is argon. These are actually the inert gases. And in case of inert gases, all the cells are completely filled by electrons. Similarly, if you talk about the magic nuclei, all the cells of those magic nuclei will be completely closed with the nucleons. When you say completely closed, it means the number of nucleons in the cells of those nuclei are such that the ability of the cell has a particular ability, and that number is found in the cell. So we simply say that the cells of a magic nucleus is closed cells. Now, what are the important evidences for the magic numbers? You will see later on, or you can say that experimental observation says that the binding energy of the magic nuclei are much larger than the neighboring nuclei. Or you can also say that the binding energy per nucleon is also very large in comparison to the neighboring nuclei. Neighboring nuclei means a nucleus whose mass number is slightly less or slightly greater than the magic nuclei. And when you will compare the binding energy of a magic nucleus and its neighboring another nucleus, you will find, or it has been found in experiment, that the binding energy of the magic nuclei is much larger in comparison to the neighboring nucleus. And so binding energy per nucleon will be also very large. And as the binding energy per nucleon is very large, so you know a large amount of energy will be required to break such a nucleus. It means if you want to separate a nucleon from the magic nuclei, you have to supply a large amount of energy from outside. From outside, you must need a large amount of energy. The another evidence for the magic number is what? It is the low-lying excited states of such nuclei are much higher in energy. It means, you know, the different energy levels of a nucleus will be at different energy value. If you talk about the excited states of the nucleus, even the lower excited state, the energy of that lower excited state is also very large. Energy of excited state, lower energy excited state is also very large. So it is also an evidence for the magic number. The another important evidence for the magic number is the number of stable nuclei with a given value of Z and N corresponding to the magic number are much more than the number of stable nuclei with the neighboring value of Z and M. As you can see in the, I have shown here in tabular form that the number of isotopes or number of isotones for a magic nucleus is large, is greater than the number of isotopes and number of isotones in comparison to the neighboring nucleus. In first table, I have actually shown what are the number of isotopes around the magic nucleus having a magic number 20. You can see, this 20 is the magic number, and calcium is the element whose nucleus is just a magic nucleus because it contains the number of nucleons equal number of nucleons means number of protons. In this table you can see I have written the value of Z. Z means number of protons for some of the nucleus, and what are the total number of stable isotopes for that nucleus I have also mentioned in this table. You can see that when we consider a magic nucleus having the proton number 20, it has the total number of stable isotopes 6. It means for Z equal to 20, for a nucleus whose in case of which Z is 20, that is, this is a magic nucleus, and for this magic nucleus the number of stable isotope is 6. But when you see its neighboring nucleus, for example, if you consider the nucleus of potassium in which there is 19 proton, then you can see that the number of stable isotope is only 2, which is less than this 6. Similarly, if we consider the argon nucleus in which the number of proton is 18, you can see the number of stable isotope is only 3, which is smaller than this 6. Similarly, for the nucleus in which a number of proton is 21, which is just a neighbor of this magic nucleus, for this the number of stable nucleus is only 1, and for Ti in case of which the number of proton is 22, the number of stable isotope is 5. Similarly, for Z equal to 23 nucleus, the number of stable isotope is 2, and for 24 it is 4. So what you see? You can see that the number of stable isotopes for a magic nucleus is greater than the number of stable isotopes for the neighboring nuclei. Similarly, if you consider another magic nucleus in case of which the number of proton is 50, number of proton, 50 is a magic number, and if the magic nucleus has a number of proton 50, it has actually the total number of stable isotope which is 10. But when you will compare the number of stable isotopes for the neighboring nucleus of this magic nucleus, you will find that this is much smaller. You can see the number of stable isotopes for a nucleus having proton number 49, it is just 1, which is much smaller than this 10. And similarly, if the number of proton in a nucleus is 51, and this is actually the nucleus of Sb, then you can see that the number of stable isotopes for this nucleus is only 2. And similarly, you can see this table for the other nucleus which is neighbor to this magic nucleus Sn. And you can find that the number of stable nucleus in these neighboring nuclei are less than this 10. So this is the specific property or the specific evidence for the magic nucleus. Similarly, in this table 3, I have shown actually the number of stable isotones when you consider the magic nucleus having the number of neutrons 20. Here 20 is the number of neutrons. You can see in this table I have written the value of n, where n refers the number of neutrons. And if our magic nucleus has a number of neutron 20, this is just a magic number, it has total stable isotones whose number is 5. It means for this magic nucleus the number of stable isotones is 5. Okay, but see, if you consider a nucleus in which the number of neutron is 19, which is just a neighbor nucleus of this magic nucleus, it has no stable isotone, no stable. The number of stable isotone, I have mentioned it here, it is 0. And similarly, if you consider the another neighboring nucleus of this magic nucleus in which the number of neutron is 20, that is 21, then you can again see the number of stable isotones is 0. And similarly, for n equal to 18, the number of stable isotones is 3, and for 22 it is 3. You can see. So what you see? The number of stable isotones for the magic nucleus is highest. This is 5 in comparison to the neighboring nucleus. Similarly, if we consider another magic nucleus in which the number of neutron is 50, then you can again see the number of stable isotone is again 5. But if we consider the neighboring nucleus of this magic nucleus, in case of which the number of neutron is 49, you can see the number of stable isotone is only 1. And similarly, if you consider the another neighboring nucleus in case of which the number of neutron is 1 greater, that is it is 51, you can see it has only 1 stable isotone. So from these tables you can see that the number of stable isotopes or the number of stable isotones for a magic nucleus is greater than the number of stable isotopes and the number of stable isotones for the neighboring nucleus. So this is a very important evidence for the magic nuclei. Now, how this magic numbers can be explained? Actually, the simplest way to explain the magic number is to assume that each nucleon in the nucleus moves freely in an orbit about the center of mass of the nucleus. If you want to explain these magic numbers, you have to consider that a nucleon revolves in an orbit about the center, or this is center of mass of our nucleus, and about this center of mass you have to assume that a nucleon revolves in an orbit freely. Actually, this is known as independent particle model, which we will discuss in the forthcoming lecture in very detail. Actually, in this case, the potential experienced by the nucleon is the average potential due to all the nucleons. All the nucleons means except that nucleon, that potential will be experienced by the revolving nucleon. Now, the question arises how we can obtain this average potential, the potential or the force which is responsible for the motion of this nucleon, how we can find the expression for that potential, or how we can find the force which is responsible for the motion of this nucleon. This is a vital question. As you know, a nucleus consists of a large number of nucleons, so it is just a many-body problem. And one can obtain, in principle, the average potential from the basic nucleon potential. But it is a very hard task. Even if one succeeds in getting the potential, it may not be possible to solve the Schrodinger equation, because you know Schrodinger equation find its solution easily or analytically only when you are talking about a single particle motion. When you talk about the two-body problem, you take a reduced mass in writing the Schrodinger equation and solving it. But if there is a large number of interacting particles, then to set up Schrodinger equation is very hard. And if anyway you can set up the Schrodinger equation, its solution will become very hard. So in practice, in this many-body problem, it is not possible to solve the Schrodinger equation analytically with this potential for the nucleon of interest to obtain the energy levels. If your purpose is to find the energy levels, this will become very hard because it is just a many-body problem. So to set up Schrodinger equation and to find a satisfactory solution of the Schrodinger equation becomes very hard. Okay? In fact, the best way seems to be just a guess at a plausible type of potential with which the Schrodinger equation can be solved analytically. It means we have just to guess the potential, not we have to find the actual potential that will be developed due to the interaction between the different nucleons, whose number is very large. And in this regard, actually, there are two important guesses to deal with such a potential. The first one is called harmonic oscillator potential, and the second is a square Bell potential. One thing you must remember, these are not the actual potential. We just guess that our nucleus and our nucleon is moving in a harmonic oscillator potential, or we just guess that our nucleon is moving in a square Bell potential. And taking the harmonic oscillator potential and the square Bell potential, we will write the Schrodinger equation for the nucleon, and such Schrodinger equation which has been written in terms of these simple known potentials, the analytical solution of Schrodinger equation becomes very easy. We can solve it analytically. So there are two guesses, important guesses, and so you can say that the suitable candidate for this turn out to be the harmonic oscillator potential and the square Bell potential. But among these two potentials, the most commonly used potential is the harmonic oscillator potential. Okay? And so in the forthcoming lecture, you will see, we will consider the harmonic oscillator potential, and we will write the Schrodinger equation in Cartesian coordinate and also in a spherical polar coordinate, and solving that we will try to find the energy levels of the nucleons. Okay? And so in this, as you have seen, this was just an introductory lecture on the nuclear cell model. I have given you an overview of the different cell model and a particular significance of the independent particle model, which is called cell model. But in a series of lectures in the forthcoming sessions, we will see first of all this independent particle model or the cell model. And as I have told you, we will consider or we will guess two potentials to deal with this problem. Never think that these potentials are actual potential in which the nucleon moves, but this is just a guess, because if you try to find the actual potential to deal with the motion of these nucleons or to find the energy levels of these nucleons, this will be a hard task, because this problem is a many body problem, because number of nucleons in a nucleus is very large, and if it is a many body problem, then to set up Schrodinger equation is also very hard, and its solution becomes almost impossible. So I hope you have understand the idea of basic idea of the independent particle model, which is called cell model, and also an idea of the evidences of the magic nucleus. Now in the forthcoming lecture, our aim will be actually to explain how we can explain that these magic nuclei exist. So by a proper theory, assuming the harmonic oscillator potential, we will try to discuss the independent particle model in the forthcoming lecture.